cell potential, free energy, and equilibrium constant. Continuing off of that, talking specifically about cell potential and concentration. So the 18.4, the fourth section of this chapter. So exactly what is a concentration cell? So it's still a galvanic cell. We're still thinking of a spontaneous reaction. But specifically, this happens when you may have different concentrations. So a concentration cell is a cell in which both compartments have the same components at different concentration. So what will impact the cell potential if there's a change in concentration? So if the concentration of one reactant is greater, we know that based off of Le Chatelier's principle, it's going to shift in the direction to kind of compensate for that, right? To relieve the stress. So here we have 0.1 molar of silver and then 1 molar of silver. So you can tell that the compartments have different concentrations. So a concentration cell is a limited form of a galvanic cell that has two equation half cells of same composition. So it's exactly the same, right? Silver nitrate, but different concentrations. And what happens is it acts to dilute the more concentrated solution and concentrate the more dilute solution by creating a voltage as the cell reaches equilibrium. So here's your more dilute, the 0.1, and the 1 molar is the more concentrated. So what happens in a concentration cell is that it's going to help dilute the more concentrated side and concentrate the more dilute side. This is achieved by an electron transfer from the cell with the lower concentration to the cell with a higher concentration. So here you can see that since the silver ions are not equal, the half reaction cell potential will not be identical, and the cell will have a positive voltage. The electrons will thus flow in the direction to equalize the concentration, which is from the lower compartment to the higher compartment. So when we have the standard cell potential for a concentration cell, it is 0 because both electrodes are identical since they're both silver ion. But because the concentrations are different, the potential are also different between the half cells. So the dependence of the cell potential on concentration results directly from the dependence of free energy on concentration. Since there's an electron flow, we use Q because we're not exactly at equilibrium yet. So we are using the exact same variation of an equation, but finding the actual cell potential using standard values. Given in a form that is valid to 25 degrees Celsius, when we plug in our values at standard, we can actually get a constant instead of always using RT. We then get that the cell potential is equal to the standard cell potential, which is found from half reactions, just like we've done. We can always find E naught through half reactions because they're all standard, to then plug into the equation and use Q from the concentrations, to then calculate the cell potential of the reaction for different concentrations that you could have. Best way to kind of put this into context is to practice. So for the oxidation reduction reaction as below, we have these two half reactions. Remember that if half reactions are not provided for you, you can always look them up based off of what's oxidizing and what's being reduced. You always have them handy for yourself. Balance the redox reaction and calculate the electrode potential and K, so the equilibrium constant. So let's first look at the redox reaction to determine what is being oxidized and what is being reduced. So I know oxygen is -2, and I have 6 of them, so I have -12. And the whole thing has to equal -12. And then I have 4 sulfurs. Well, this would become 4 sulfurs is equal to 10. So plus 12 on both sides would be 10. So sulfur is therefore plus 5. So I have plus 5 and -2 for one single sulfur and oxygen. Chromium is plus 2. Chromium 3 plus is plus 3. And then again we go here. So 2 sulfurs plus 3 oxygens is -2. So 2 sulfurs would be minus 3 times -2 is 6 is equal to -2. 2 sulfurs will be 4. Sulfur is plus 2. So plus 2, minus 2. So then oxygen doesn't change, and your sulfur went from plus 5 to plus 2. So what is happening to that? It is being reduced, and chromium, since it's going more positive from 2 to 3, it's being oxidized. So this is reduced, this is oxidized. So therefore, what do I have to do to my half reaction of chromium? I flip this, right? And I'm going to write it up here to get chromium. And then I have to also multiply it by 2 because I want to balance the reaction. So I would get 2 chromium 2 plus makes 2 chromium 3 plus and 2 electrons. Then you can see your cell potential would then be positive 0.50. And your 2 electrons cancel out. And you're left with the remainder of your balanced redox reaction now. And then what would be your cell potential? The sum, so 0.50 plus 0.17 is 0.67 volts, and since it's positive, it goes into context with our galvanic cell. It is spontaneous. And now we want to figure out equilibrium constant. Well, we already know that our electrode potential relates to our equilibrium constant in the following equation. So I have everything I need, and I can rearrange to solve for K. So if I were to cross multiply and do N over 0.0592, I would get that the log of K is equal to N times this electrode cell potential over 0.0592. Log K would then be, what would be my N? How many electrons do I have here? 2 electrons, 2 moles electrons, times my electrode potential, 0.67 over 0.0592. That comes out to be 22.6. Then to get K, you do the inverse of log, and K is equal to 4 times 10 to the 22nd. Very, very large K, very product favored, which makes sense because the electrons are going towards the right, towards the cathode to make this reaction happen. So because the cell potential is sensitive to the concentrations of the reactants and products involved in the cell reaction, measured potentials can be used to determine the concentration of an ion. So we know that we can use a pH meter because it has that specific component of a glass electrode. And a glass electrode potential changes depending on the concentration of the hydrogen ion in solution into which it's dipped, and that's how we can measure the pH. It contains a reference solution of dilute hydrochloric acid in contact with a thin glass membrane. And then we have an ion selective electrode, which is just a glass electrode that can be made sensitive to very specific ions such as sodium, potassium, or ammonia by changing the composition of the glass. So we can figure out the pH in using certain equipment or even going from different reactions and calculations. So I wanted to do an example problem together and then let you try one on your own. So let's say that we are given the following electrochemical reaction. So we have copper 2 plus, here's my cell. And I want to calculate my cell potential, my standard Gibbs free energy, my total Gibbs free energy for the reaction, and my total cell potential. Notice the difference. Here's a good practice of the differences between standard and not standard reactions at 25 degrees Celsius. So first thing, I know here's my anode and here's my cathode. Anode is oxidizing, cathode is reducing. So I'm going to look at my half reactions, and I find that if I flip it for cobalt, I'll get cobalt is cobalt 2 plus 2 electrons, and my cell potential comes out to be negative 0.28. And for silver, I get silver ion plus an electron gives me silver, which is then the cell potential of 0.80 volts. I then can get my two equations together. I would have to multiply the bottom by 2. I would get cobalt plus 2 silver ions makes cobalt 2 plus 2 silver solids. And what would be my cell potential here? Oops, 2 electrons cancel out. My cell potential would be the sum, which would be, what would be 0.28? This should be positive because I had to flip it. 1.08 voltage. Perfect. So I now know what my net cell equation looks like. I calculated my first part. I got done with my standard cell potential. Well, I know that my standard Gibbs free energy is equal to negative N Faraday's constant E naught cell. So what's negative N? Negative the amount of moles that you have. Well, you have an interchange of 2 moles of electrons, and then Faraday's constant, 96485 coulombs per mole, times your voltage, 1.08 V. That is then equal to negative 2.08 times 10 to the 5th joules. Now, Gibbs free energy is always in kilojoules, so you would convert dividing by 1,000 to negative 208 kilojoules. So you have your standard cell potential, standard Gibbs free energy. So then you know, well, I can relate my total free energy in my reaction with my standard. Total free energy is equal to my standard for the reaction plus my R constant, temperature, and ln of Q. Well, let's first look what would be Q. Q is products over reactants. We know that we do not include solids or liquids, only aqueous and gases. So based off of my equation up here, I only have 2 aqueous substances. So I will have cobalt 2 plus over silver plus, that's squared. So that would be those numbers plugging into that equation. So then let's plug everything in. Because my R is in joules, you either convert your R constant or you convert your delta G back to joules. It doesn't matter. I'm going to use my delta G naught as my joules. Plus my R, 8.314 joules per mole Kelvin. Temperature, 298.15 Kelvin. And then my Ln, my products over my reactants. Now my cobalt is 0.0155. And then my silver is 1.5, and I have to square that. So you plug everything in, and your Gibbs free energy of the reaction is negative 1.96 times 10 to the 5th joules. And we usually want kilojoules. So we have negative 196 kilojoules. Now we have one more part left. Now I can use my Gibbs free energy of the reaction for my total cell potential. Cell potential is equal to Gibbs free energy over NF. Well, I know I have negative. There are 2 negatives. Again, what do I use? Since my Faraday has coulombs in it, it works with a joule, so I want to stay in joules. Over 2 moles times 96485 coulombs per mole, which then gives me joules per coulomb, which is a volt. So I would get 1.01 joules per coulomb, which is 1.01 volts. And that is why we want to leave joules, not kilojoules. And then we take it step by step to figure out exactly what we're solving for. Now, a good thing to do is just to have these equations written out on the side so you can kind of figure yourself out a plan to know exactly how to solve for each individual component.